Hello everyone. First of all, thank you for tuning into this talk. My name is Morten, and today we're gonna talk about teaching computer architecture through visual and interactive simulators. Specifically, we're gonna take a look at an application called RISC, which is an educational computer architecture simulator built around the RISC-V instruction set. And it's a project that I've been working on for now a couple of years and has grown to be used in quite a few universities around the world. Okay, so just briefly about me. I'm right now a master's student at the EPFL in computer science. Before that, I had a short stint at ARM over in Cambridge. And before that, I did my undergraduates in electrical engineering at the Technical University of Denmark. Okay, so what are we going to go through today? First of all, we're going to take a look at what are typical for educational simulators in the computer architecture world, and some motivational slides for why RISC is what it is. Also, this is going to be a quite demo-heavy talk where we're going to take a look at how we would use RISC in an educational scenario. So the first demo we're going to go through is just an overview of RISC. We're going to see how to use it, and we're going to see how to use different processor models to illustrate different concepts of computer architecture. Then we're going to dig a little bit deeper into RISC and see what's actually inside. Specifically, we're going to take a look at a project called VSRTL, which is a spin-off project of RISC. And then the second demo we're going to go to is C integration in RISC. So how can we write C programs in RISC and actually simulate them? And secondly, on cache simulation, again, we can write C programs and then see how these affect different cache geometries. Okay, so initially teaching computer architecture. We're going to have the point of view of the way that most people get introduced to the topics of computer architecture, which will be through an undergraduate course at university. So what are typically taught? What's the typically taught subjects during such a course? Well, we would get introduced to what is an instruction set, and then a course will choose whatever instruction set that they choose to teach. So we're going to see what that is, and then we're going to do a bit of assembly level programming just to get familiar with the instruction set. But the brunt of the course will be on microarchitecture. So mainly, what is a processor and what are the core building blocks of a processor? So typically, we would start out with seeing what a single cycle processor is. Then we see that that's really not performant enough for what we need. So we move on to pipelining that single cycle processor. But with pipelining comes issues such as hazards, which we need to have a method of resolving, either through use scheduling or modifying our data path. And we can also increase our performance, such as by implementing forwarding. And typically, there would also be a substantial part of the course devoted to memory systems, particularly caches. So what are caches? Why do we have them? And what are the different design parameters that we're working with? Now, alongside this, a computer architecture course will typically rely on simulators, either one or multiple simulators. For actually, after we've been presented with these core concepts, then we need to go and actually exercise our knowledge and play with it a bit. And there's already a bunch of very nice educational simulators and non-educational simulators listed on the RISC-V.org website. Here I've listed a few of them and three categories which I think are quite important for the educational aspect. First of all is the online simulators. These are super good for the sort of initial contact case, because you can just go to a web page, there's zero setup, you can just go there, write some RISC-V assembly code, and then try and see what happens. Then we have the class of the functional simulators. So these are really powerful simulators that can efficiently execute binaries, but probably they aren't really the simulators that we would go to as the sort of first point of contact. And then we have the visual simulators. One example is RISC-V, but RISC is definitely also in that category, which are really good because we can actually investigate the data path during execution. We can see how the data path reacts to different programs that's going through the processor. So the main idea here is that why don't we have a single application to experiment with all of these core concepts that we see on the left side while unifying some of these simulator capabilities on the right side? and just try to not have to go through maybe 2 or 3 different simulators in a course, but we can stay within a single application. So this is motivation number 1 for RISC. Number 2 is typically when you see a course on computer architecture, we will also use some form of educational book. And in these books, when we're going through how to pipeline a processor, there will typically be examples such as what you see here. So this is a snapshot of the data path at a single clock cycle executing some program. And then what we want to be able to visualize here is how different signals and how the state of the data path is reacting to the program that is currently loaded into the processor. Now, the obvious issue here is that this is a print media. So first of all, we have to devote, as you see, a whole page just to visualize 2 clock cycles of a program execution. But furthermore, this might be a good example. The program that's in it, loaded in the processor, might be a good example for some people, but other people may want to try and write their own program to just really nail and drill in this understanding of what's going on in the data path. And this is, of course, not really possible in print media. So motivation number 2 for RISC is really that we want to be able to generate these visualizations of the data path using an arbitrary program that the programmer or the student or whoever who's trying to learn about RISC-V decides to write. And now the third motivation here, this is more of my own personal opinions about what makes a good educational simulator. So I think that the simulator should really make you want to explore RISC-V, right? So you've had a course or you've read in a book about what is RISC-V and what is entry-level computer architecture, and then you actually want to go out and exercise this knowledge. And I really think that the simulator should be sort of an ally in that situation and make it easy for you to go out and explore these things. And this kind of ties into the second point here. The educational simulator is typically the first point of contact when we're learning something technical, right? And so I fear that if this first meeting between sort of theory and practice is not enjoyable, then we might end up losing some people in that. So I really think that we should try and make it enjoyable and fun to use these educational simulators. So all of these previous slides and this slide can then be summed up to a few key requirements. I think there should be little to no setup in such a simulator. We should try to eliminate sources of frustration. So ties into what I just said here, but also, for instance, I think we should try to strive at having graphical user interfaces instead of command line user interfaces and things like this. We should try to make it visual for the exact same reason that we include pictures of the data path in books, because people also learn through their eyes. But despite all of this, we should also try to make it a little bit capable. Right? We don't want to make a toy here. Ideally, this first point of contact educational simulator should serve as a bridge between someone coming in with almost no knowledge of RISC-V or computer architecture, and then take them through to a point where they can transition to these more functional simulators. Okay, so with these motivations in mind, what is RISC? So RISC can be summarized as being a visual processor simulator and assembly editor for the RISC-V instruction set. Some of its capabilities are that we can simulate a variety of in-order architectures, which we're going to go through later. All of these implement the RISC-V 32-bit INM instruction sets. In terms of editing, here we have an integrated assembly editor, an assembler. We can go and interact with the memory, and we can also see an animation of the data path during execution. And then we can also experiment with some higher level concepts. We can take a look at cache simulation, and we can take a look at or RISC supports C toolchain integration, both of which we're going to see in the second demo today. So these are some of the universities which I'm familiar with that have been using RISC or are currently using RISC. This is, of course, not just good for to know in the aspect of RISC, but also that we can see that RISC-V is really gaining traction out there in terms of being a really viable option for teaching computer architecture with. Briefly, I also just want to show a timeline of the program and the project. I started back in 2017 where RIPES basically just started as an instruction set simulator I had to write for my first undergraduate course on computer architecture. But then I kept on working on the program, resulting in around 2018, we had let's call it a prototype of what RIPES is now, where we had a visualization of a 5-stage pipeline with a built-in assembler and editor. Now, at this point, the program was still in a very rough state, but interestingly enough, there was, I'd say, quite a bit of interest from different teachers and universities who actually took an interest into this kind of educational simulator. So the issue was that, as I said, at this point, RIPES was in a very prototypey state, and to develop it into something more viable, we really needed a proper method of describing these visualizations of digital circuits. And so that spun off into a separate project called VSRTL, which we're going to take a look at later, which is basically a circuit visualization framework. Work on that sort of finished here in early 2020, which allowed us to move the sort of simulation backend in RIPES over to VSRTL, which also meant that we could now have multiple processor models in RIPES. And then here around mid-2020, we managed to put out cache simulation and C toolchain integration, again, which we're going to see in the second demo. So before we go into the demo, I just want to go through the user interface with you so that we're familiar with what we can see in RIPES. This is the editor view, where you'll have 2 tabs containing code. On the left, you have your source code, and on the right, you have your disassemble executable. Now, the reason for why you have this kind of view is that I feel that there's quite a bit of learning to be done already at this point, right? Because even though we take assembly as being a very low-level form of our program, we still have some abstractions there, right? We can use pseudo instructions, we can refer to labels and things like this. Whereas if we take a look at the assembled program here on the right, we see that all of this has been replaced with actual executable instructions. So already there's a bit of learning to be done. Up here, we see the simulator controls. So it's possible to clock the pipeline, but equally important, we can also undo clock cycles. So we can basically find an interesting point during execution and then go back and forth around that point and see how these points or that point in the execution affects the data path. Finally, down here, you see stage contents. So what this is that we, for instance, for a 5-stage pipeline processor, we might have 5 different instructions on the fly at the same time. And this is annotated in this in the editor by these stage content annotations. So if you want to, you can follow along with program execution just in this page that you see here. Okay, now moving on to the processor. This is sort of the main tab or main view of RIPES. In the center here, we have an animated data path where we can see the circuit being animated as we're executing our program. The main things that are animated are, for instance, we can see the operands of multiplexers. So where we're currently getting our operands from in the data path, we can see whether a register is being clocked right now, or maybe if a register is being cleared, and things like this. We can also enable to see labels if we want to monitor a value on a given port and all this kind of stuff. Out here to the right, you have a view of your registers, and you can also select how you actually want these values to be displayed. And finally, we have our instruction view here. So this is sort of a condensed version of what we saw on the previous page, where we can see where we are in the program right now, and we can also set breakpoints if we want to. Also note that in RIPES, it's possible to generate these laundry diagrams, which, if you're familiar with the literature and the books typically used to teach these concepts, these are used quite a lot as well. So on the left, we have our instructions in the program, and the columns will represent different cycles during execution. And so the annotations of the stage names here will show sort of how each cycle propagated through the processor, where it's also possible for us to annotate when a stage was flushed or when we are stalling a stage. Finally, we have the memory tab here. To the left, we have a scrollable memory view. So this gives you a view into the entire address space, and you can go wherever you want to and inspect the simulator memory at any time. And to the right, we have our cache simulation area. This here is a cache animation where you see that we draw the cache and the current contents of the cache. The yellow column and yellow row will illustrate how we're currently indexing into the cache, and where these two meet, that block will be either green or red, depending on whether it's a cache hit or a cache miss. Up here, we then have a cache geometry configuration and cache policy configuration. So in geometry configuration, we figure out how many lines, how many ways, and how many blocks we want to have in our cache. We're going to experiment with this in the second demo. And then to the right of that, we have the policy configuration. So is it a write back? Is it a write through cache and stuff like this? And then finally, we have some cache access statistics here so we can see our hit rate, and we can also get a plot of this hit rate over time so we can see how this develops and whether we improve in our hit rate during execution of possibly a large program. Okay, so that was the overview of the user interface. What we're going to go through now is the demo of RIPES, the initial demo here. So I'm going to load up an example here. It's a very simple program where we're loading a word at position A here in memory. It's just 123, and then we're adding 1 to that. So that means that we would expect when this program has finished executing that we have the value of 124 in register A0 or X10. Okay, so let's move on to the processor here. We're just going to simulate this on a plain 5-stage processor that implements forwarding and implements hazarding. So I'm going to step through this program, and we see here that, for instance, where we get operands from are changing at each cycle. And at this cycle here, we then see that a stall is being inferred. Right. The reason for this is that we have a memory hazard. This ADDI instruction here is dependent on the memory that's being loaded from memory. Sorry, the value that's being loaded from memory by this load word instruction. And so to actually resolve that dependency, we have to infer a stall here. Now, let's say that I was just being introduced to these concepts and I wasn't really sure about why that stall or how that stall actually came about. Well, this is the point of being able to undo clock cycles. So at this point in execution, I can undo this cycle, go back 1 cycle in time, and then we can take a look and see that right now this IDEX register, the stage separating register, is being cleared in the next cycle. So this is what infers a NOP. And this clear here is being asserted by the hazard detection unit. So just for good measure, let's try and fully execute the program here, where we get the expected value of 124 in register A0. Now, let's try and take another processor where this wouldn't execute correctly. For instance, we can take the 5-stage processor without forwarding or hazard detection. So this processor is basically just a single cycle processor where we've added stage separating registers in between some of the components. And now let's do the same thing. The program is loaded in and we can execute. And now at this point in time, we would assume, as before, that the clear here would be enabled to infer a stall, but it's not because we don't have a hazarding unit. And so we just execute all of the instructions. And going through to the end here, we see that we end up with a value of 1 in register A0, which is obviously not the sort of semantically correct value to end up with here. And then at this point, someone playing with this or trying to learn about this would then either have to, for instance, user schedule instructions by inserting knobs to account for the stalls that would be needed here, or, of course, change your data path over to the 5-stage processor. So, yes, this is an example of how someone would use RIPES to play with these concepts. Okay, so let's now take a look at what's inside RIPES. And to do that, we first need to take a step back in time, back to this point of the prototype of RIPES, as I mentioned earlier. during the timeline. So for this initial version of RIPES, there were some key lessons learned. First of all, in terms of circuit description, we really needed a correct and versatile simulation framework. This would allow us to easily modify the designs of the whatever visualization that we want to present, but also allow us to hopefully have multiple different processor designs to really be able to illustrate each step of the cycles that we go through when we learn about these microarchitectural concepts. Then also, in terms of graphics, the circuit visualization that we generate, this is an obvious point, but that should obviously be generated from the circuit description. Also, having a more well-defined graphics framework would allow for things such as interaction with the circuit, where we can highlight wires, we can show and hide components, and all of this stuff, just to make it a little bit more interactive and less static. And then in terms of simulation, apart from it just being a correct simulator, we also need the ability to step back and forward in time. So the reason for this is exactly what we saw just before in the demo, that it allows us to go in and investigate interesting situations that occur in the pipeline. So we can step back and forth between this sort of sliding window of interest. Now, the interesting thing here is that all of these things that I just described above, they don't really require us to be simulating a processor, right? It can actually be fully decoupled from that notion of simulating a processor. It's only a matter of simulating digital logic. And so the idea is that what if we can create a framework to provide all of the above and then base RIPES on that? So that's the idea of VSRTL. VSRTL stands for Visual Simulation of Register Transfer Logic, which is a framework for describing cycle accurate simulators, which provides an automatically generated visualization of the simulated circuit. And that's what we're going to take a look at now. So what is VSRTL? VSRTL is basically built in 3 layers, where in the bottom layer we have what's called VSRTL Core. This is a very simple hardware description language that's embedded inside C++ that contains all of our simulation algorithms, but also circuit primitives such as ports, entities, wires, and signals. These are things that we expect in other hardware description languages as well. Now, on top of that, we have VSRTL components, which is basically a standard library for VSRTL that implements different kinds of logic gates, registers, and multiplexers. And now you see here that we have explicit registers and explicit multiplexers. That's because circuits using VSRTL to describe themselves, they must explicitly infer all of the logic that they want to have visualized. So it's not like an elaborated language or synthesized language. And then up top, we have VSRTL graphics. This is where we have all of the component widgets. So how do we visualize each of the entities that we have in our digital circuit? But it's also where we have all of this logic for reflecting the underlying simulator stage changes. And we have our visualization plate and route routines. So these can be seen as like adapted EDA algorithms, where we optimize for, visual niceness instead of just having a small area. And so where do we then place our circuits and the descriptions of our circuits? Well, that's in between VSRTL components and VSRTL graphics. So when we write our RIPES processor models, we don't actually have anything to do with the graphics. We just describe the underlying hardware, and then we hand that off to VSRTL graphics, and then this can index the circuit and generate a visualization of it, and also interact with the simulator. So it's important to note that there is quite an opaque interface between VSRTL graphics and VSRTL components and core. So this interface basically only demands the underlying simulator to implement routines for circuit traversal, state change signals, and things like this. And this is a very intentional design decision, mainly because that no one needs another hardware description language. So for me personally, VSRTL Core was an interesting experience trying to explore some of these algorithms, but we should obviously be able to use commonly used hardware description languages where we already have nice circuit designs and then simulate those, right? And so ideally, VSRTL graphics, it just expects some simulator backend adhering to its interface, and then it can generate these visualizations. I hope that in the future, this design decision will amount to, for instance, if we get an FIRGL parser or a simulator backend, then this would implicitly mean that we can give Chisel a simulator with visualization. So taking these lessons learned from RIPES and then totally generalizing it into whatever circuit that people are writing in Chisel. So whether this having visualizations of people's circuits will be useful, we'll have to see, but I think in any case, it's a very nice novelty factor just to be able to see your circuit and to see what you just described light up during simulation. To me, it's just a cool thing. So I think that's a fun thing to have. Okay, so after we implemented VSRTL, and what did that give us in terms of the second version of RIPES? Well, if we look at RIPES version 2, which is what we're presenting today, the main thing is that we can now have multiple different processor models. So RIPES right now ships with 4 different processor models. We have a single cycle processor, a 5-stage processor, a 5-stage without hazard detection, and a 5-stage without forwarding or hazard detection. And now the reason for why these 4 processors were chosen is because this is a typical sequence of processors that we're going through when we're learning about computer architecture, entry-level computer architecture, right? So the idea is that having these processors available, you can now go in at any step in time while you're learning about these concepts and actually go in and write programs and execute them on these kinds of simulators and see why your programs work or why they don't work, and then directly go in and do whatever you need to do to actually make those programs execute correctly. Now, secondly, having VSRTL allows us to have different views for each processor models. I only showed you the standard views before, but just in a minute, we're going to go and take a look at the extended views here. So the extended views typically contains the control components, forwarding and hazarding units. The reason why these are not included into the standard views are because that they do have a lot of signals connected to them, and so there is a fear that this may clutter the view, and for people who's just getting into the topic, it might be better to just have the core signals visible. Also, in the extended view, we can see port widths. So this is interesting for those who wants to see where we may be spending more or where we're spending less resources in our circuit. Also, this allowed us to be interactive. I mentioned this briefly before, but we can enable labels for all ports in the entire circuit. So, for instance, as you see to the right here, we want to monitor what are the input operands to our ALU. Well, we can just enable labels here, and then we can take a look at what's going into the ALU at any point during execution. Also, in terms of wire highlighting, especially in the extended views, it can be a bit confusing to see how wires actually route and where they originate and where they terminate. So, for instance, if you're interested in seeing where does this input operand to my multiplexer here connect to, well, you just click on the wire, and then you see that in this case it comes from the write back stage. Right. So this is just to make it as interactive as possible. And then finally, it allowed us to do reversible simulation, which again, I think this is a key good thing here in RIPES, that we can go in and actually really focus on these situations of interest. Okay, so that was VSRTL. Now we're going to go into the second demo, where we are going to see how we can use C inside RIPES, and finally a little bit on cache simulation inside RIPES. Okay, so first of all, I'm going to change to the 5-stage processor again. And let's take the extended view this time, just so you can see it. And now, as I said before, if I'm in doubt about where some signal connects to, maybe I want to figure out the output of my write back stage, where does this actually connect to in my data path? You know, I just click it, and then I can see all of the termination points. Okay, heading back to the editor, I'm now going to go and select a C program here. it's not that important what this program does. Briefly, it's a sort of an approximation of pi. The interesting thing here in terms of learning is that we are using floating point operations, but as I mentioned before, these processors implement the RISC-V 32 I and M instruction sets, so we don't have native floating point support. What this means is that in the compiled program that we are executing, we will have to rely on the runtime library routines to enable support for floating point arithmetic on an integer machine. Okay, so this is the program that we want to execute. Now I've registered a bare metal compiler with RIPes here, so I can just go ahead and click compile. Just a second. I need to remove this. Here we go. I can just click here. And all of the building and loading the program into the simulator is automatically done by RIPes. We don't have to think about any of that. Now, what you see here is then the entire very large program, because we are loading a bunch of standard library and runtime library stuff in, but we have the view here. Now, for those familiar, this view that we see here is highly inspired by Compiler Explorer, where on one side we have the C program, on the other side we have our assembled program that we're going to execute. Now, the only difference here is, of course, that this is directly tied into a simulator, right? All right, so what I'm going to, just to show this stage contents here, I'm going to start auto-clocking the circuit here. So it just clocks every 200 milliseconds or so, and then we can see the instruction starting to propagate through the data path. As you can see here, we could also continue to follow the execution of the program in this editor view here. All right, so moving on to the processor, this is how it looks. We have an animated data path, and instructions are flowing through the circuit. Now, this is a very large program, so we don't have time to auto-clock through it. So we can also just run the simulator. What this means is that we stop updating the graphics and we just let it run as fast as possible. So we're going to do that. And then we see that there's a bunch of stuff being printed to the console here. And in the end, we should have our approximation of pi here. But now let's take a look at this execution info tab here. As you can see, we have an IPC count here, instructions per cycle. So we see that this is less than 1, which is what we would expect for such a pipeline processor, because we have to spend some cycles on having these flushes and having these stalls, which means that we can't have an instruction retiring every clock cycle, which then results itself into an IPC of less than 1. Again, this is also an important learning thing, because this is a key measure in computer architecture. All right. For the next simulation, we're now going to go into cache simulation here, RIPes. Because some of these programs, or the program that we're going to execute has quite a few instructions we need to go through, I'm going to select the single cycle processor here. So while I could also just keep on executing the 5-stage processor, this one is a bit more performant, so it takes less time to go through the program. And at this point, we don't really care about the pipeline anymore. We move on to the memory system. So we just need speed at this point, or we basically just need an architectural simulator. Okay, so moving back, I will go and select the matrix multiplication example here. Now, again, this is a very simple program where we're just multiplying two 20 by 20 matrices together. And yeah, that's what we are doing. Now, notably, we are providing our own startup code here, which means that we're not relying on the standard library in this case here. So I can go in and tell to the linker that I don't want to link with the standard library, and then compile the program. And this program here is significantly smaller than what we saw just before. Okay, so we have our program, we have our processor, and now we're going to go to the memory tab. Just briefly, we see here that we have the interactive memory view, where right now I'm scrolling through the memory and I can go anywhere where I want to. Taking a look at the caches then. First, we're going to take a look at the instruction cache. I'm going to start the program executing here, and then we can see that the cache is slowly starting to fill up, right? And while we're executing through the program, we see that we have more and more in the cache, and ideally our hit rate should also go up assuming that we're maybe executing some tight loop and we're able to have all of the loop instructions in our cache. So let's just get a few more cycles done. And now we see that we're probably executing a loop right now, and that is the reason for a very good hit rate, or at least increasing hit rate. So I'm going to stop the processor again. Let's take a look at how this hit rate then evolved over time. So this is what this graph shows, our hit rate over time. And we could, in theory, choose any of these things to graph and then see how this actually, yes, evolved over time. Now, for going and trying to play with the cache configurations, we're going to take a look at the data cache instead. We're going to go through 3 different configuration examples to illustrate how different configurations, which contain the same amount of data bits inside, have 3 different hit rates. The first configuration that we're going to take a look at is just a plain 32-entry direct map cache. Also note that the 3 examples that we're going to go through now all have 4,000 bits of data in them. All right, so this is our direct map cache. I'm then just going to go and execute the entire program, and then we're going to take a look at the hit rate. So we're executing, and that was the program. We see that we have a hit rate of 94%, which is pretty decent, but let's see if we can do better. Now we can go onto a whole other ballpark and take a fully associative cache, a 32-entry fully associative cache. Now this would most likely not be a realistic L1D cache in real life, but we have it here as an option, and we just want to experiment with the concepts, right? Again, note that we have the same amount of data bits inside the cache, so we're not storing more. It's just a different way of indexing into the cache and containing values in the cache. So we're going to do the same thing. We're going to execute the entire program, and then we see that we have a hit rate of 98%. That's pretty decent, definitely more than we saw just before, but as I just said, this is probably not a realistic cache. So can we find a happy medium between these two? Yes, we can. Let's try a 32-entry two-way set associative cache. Now this is definitely a realistic cache configuration. We're going to do the same thing again. We run the program, and then we see that we have a hit rate of 97%. So definitely better than our direct map cache, only slightly worse than the fully associative cache, but again, this is something that we could actually realize. And now the interesting thing here is that I could do this with any C program, right? I could go in and see what is my IPC on any of the architectures that support it, and then I can go in and just play around with how many cache lines do I have, how many ways do I have. If I make the matrix larger here, how does this affect the cache configuration here? And maybe I need to increase the number of lines to actually have the same hit rate, and all of these things. Just trying to exercise all of the core concepts. Okay, so that was demo number 2. So let's talk about the future and going further with RIPes. There's definitely some low-hanging fruit already out there. Here I'm specifically thinking about I/O. So you could imagine that we have some LEDs you can write to, or some screen that you can write to inside RIPes. But I think more importantly would be that we have branch prediction that's being visualized and configurable very much in the same way as we already have the cache view, right? So you can change the size of your branch history table if that's your branch predictor, and you can see how these different configurations affect your performance. Now, these are fairly simple concepts, but what about if we take the philosophy and the ideas of RIPes and actually go a little bit beyond these basic things? So we could take a look at out-of-order processes. Now, this is not an easy thing because we don't have the sort of the convenience of the entirety of academia basically agreeing on in-order 5-stage pipelines being the thing that we teach during an undergraduate course. So with out-of-order processes, we have a lot of design variations, and we have a lot of things, a lot of variables that we can tune in terms of how we want to do our design. So it's very hard to just select a single or two or a couple of visualizations that we want to put in the program and say that, okay, this is what you're going to teach, because there's so much variability in these designs. But I still think that there's something out there where we could try and maybe modernize some of these tools. And then I hinted to this earlier, but we also have VSRTL, and I think it could be really interesting to either take VSRTL in its current state or just take the ideas of this and couple it with, for instance, FIRTL to really try and bring the option of these visual simulators to sort of an already established hardware description language. Okay, so that was my presentation. RIPES is on GitHub, and there's a couple of pre-built binaries for all of the major operating systems of RIPES there. So if this was interesting to you, you can just go there, download it, and try it out for yourself. And if you have any questions for me, feel free to send me an email. And yes, again, thank you very much for listening.